Hi, I'm Mario Inciosa, a data scientist in Microsoft's Azure AI Customer Engineering team. In this recording, my colleagues and I will present a summary of our paper on generating and evaluating simulated medical notes. Since healthcare data contains highly sensitive personal information, there are many restrictions on sharing and working with such data. To test healthcare software, it's very useful to have a source of simulated medical notes that is not subject to these restrictions. Here, we provide simulated tabular medical record data generated by the open-source Synthea system to a state-of-the-art generative language model, Microsoft Turing NLG, which then generates a semantically consistent history of present illness narrative. Such generative language models represent a new software paradigm where achieving natural language processing tasks such as free-form language generation, question answering, and abstractive summarization reduces to an exercise in composing a suitable natural language prompt. Parameters control the language generation process, allowing trade-offs between diversity and consistency. Using 4 diverse quality metrics, we compare the output produced as a function of a control parameter and find that there is an optimum parameter value for a given balance between objectives.
Thank you, Mario. Let's look a little bit at the experimental setup that we used in this study. Let's look at the prompt design first. On the left side of the slide, you can see one example of a prompt. Each prompt contained the same set of structured facts and an example passage of a history of present illness, also known as HPI. To have the NLG model generate more HPIs, we would append a new set of structured facts. The task of the model was then to generate a new HPI based on these new structured facts. Let's look at some example output. At the top, you can see the end of the prompt showing structured facts about Amber Hand, who was diagnosed with a fractured forearm. Below, you can see the HPI generated by the NLG model. You can see that the model does a good job including the structured facts. We highlighted these in green. But you can also see that the model fills out the story by adding information that was not part of the structured facts. Here's our data generation and evaluation flow. We used Synthea to generate simulated patient charts. We created prompts for the Turing NLG model so that it could generate HPI passages. We repeated this process for different settings of the hyperparameter tau p for the Turing NLG model, which affects the creativity of the generated HPIs by allowing the model to include low probability words in the HPIs. We then evaluated the performance of the Turing NLG model along 4 different evaluation criteria. Alexandre, do you want to talk about the first set of results?
Thanks, Wolfgang. Now let's take a look on how we used diagnosis classification tasks to evaluate the agreement between facts in the generated HPI text and facts given by Synthea. We designed 2 classification tasks where we try to predict the diagnosis given by Synthea using the generated narratives as features. The first one is a multi-class classification task from which we try to identify the major types of inconsistencies by looking at the classification errors. We also designed a series of binary classification tasks where we have different parameterizations controlling the diversity in the generated narratives, allowing us to quantify the influence of that parameterization by analyzing the classification performance given by each model. And for all these classification tasks, the approach was to fine-tune a pre-trained BERT model for text classification. In our first evaluation, we found 3 major inconsistency patterns. We saw examples of generated text with facts unrelated to the diagnosis, making it impossible even for an expert to link those facts to one of the possible diagnoses. We also saw examples of facts in the text that could be linked to one or more of the possible diagnoses, but those facts were not sufficient for one to reach a conclusion. And finally, we also saw examples of facts in the text that could correctly represent more than one of the possible diagnoses. And in our second evaluation, we observed a drop in classification accuracy as we allowed the generated text to be more diverse.
Thanks, Alexandra. Pattern matching and entity recovery are the next methods we are discussing. In use cases that we know the pattern that typically appears in the real text, pattern matching is a reasonable method for evaluating the quality of the generated text. We quantify this by measuring the fraction of passages containing those patterns. Here our example is a fracture of ankle case, and we extract common symptoms and causes for this diagnosis. The right side diagram confirms the higher appearance of relevant terms like pain and swelling compared to hypertension, which is an irrelevant term that appeared in the prompt. This is in line with our expectation. In clinical NLP, it is a common interest to extract name entities like demographic or medication information. Now, our question is that to what extent these entities in the simulated nodes agree with the prompted information we queried for. We use name entity recognition API from the text analytics for health to extract age and gender from the passages and compare them with the ones in their corresponding prompt. We see that with higher top P, the matching ratio gets worse. This guides us in controlling the outcome by changing the hyperparameter top P. In the following slides, Bob will discuss this further in depth.
Thanks, Miriam. Repeating text is a common failure mode for NLG models. Since the model generates new text based on what has been written so far, once the output begins to repeat itself, it can fall into a trap. This zoomed-in view of a t-SNE plot shows how we can use semantic embeddings to detect repeats. The points represent individual sentences. They're partially transparent so that single points appear pale. Brightly colored spots indicate multiple sentences plotted on top of each other, which means that they have very similar embeddings. Approximate repeats are close together, but not exactly on top of one another. Here we see alternation between two clusters of similar sentences. The orange sentences are in one cluster and the green ones in another. By noting which cluster each sentence belongs to, we can see if a passage contains repeated sentences by tabulating the cluster IDs. Here we plot the fraction of generated passages that have no repeated sentences. The rose-colored line uses a very small distance threshold, so we only consider sentences to be repeats if they're very similar, while the teal line uses looser clusters, allowing more approximate repeats. High values of top P reduce the tendency to repeat sentences. We've looked at several measures of diversity and consistency in synthetic medical notes generated with the Turing NLG model, focusing on effects of the hyperparameter top P. Both our ability to predict the diagnosis from the synthetic passage and the ability to recover prompted facts from the passage decline as top P increases, but the fraction of passages free of repeated sentences improves. An optimal top P value should balance these opposing trends. Future work will need to address a variety of semantic errors, some kinds even people without special training can recognize. This creative phrase, native Caucasian, probably reflects Cynthia's abbreviation of American Indian or Alaska Native to just native, which may have confused the NLG model. We worry about poor Mr. Nicholas here when he's discussed in the past tense. We just wanted to break his leg, not kill him. Finally, Orthea is 5 years old. Makes you wonder how long she's been married. But the more complicated issues require domain knowledge. Replacement elbows, for example, are not like kidneys. We don't typically think of a waiting list for elbows. Also, it would be very awkward to have your ankle in a sling. Our work so far on programmatic evaluation helps to weed out some obvious problems and sets the stage for supervised ML approaches. Our next iteration will require close collaboration with medical experts to develop structural rubrics for scoring how well the generated histories meet criteria for realism and consistency. Our physician colleagues can then use these criteria to label examples for training and testing ML classifiers that will help us to optimize prompts as well as hyperparameters.
Thank you, Bob. We would also like to thank the workshop organizers and attendees. We hope you found this video interesting and informative.